Hi everybody and welcome to a new video in the Monster Text-to-Speech and Voice Cloning course. In today's video we're going to look at how machines can process text for text-to-speech. First we're going to jump back into a traditional text-to-speech pipeline and see how things work here. We start with a text. It could be a sentence or a series of sentences. Then what we do is we transform those sentences into phonemes. Now, if this concept of phonemes is something that you don't know, probably you haven't watched my previous video, and I highly suggest you to go check that out first, because otherwise what's going to come next is not going to make much sense. Good. We now have our phonemes, which we input into an acoustic model. The acoustic model takes the phonemes and spits an acoustic feature representation of those phonemes. For example, a MEL spectrogram. Next, what we do is we take that MEL spectrogram and we pass it through another model that's called a vocoder that takes the spectrogram in and spits the final waveform. That is the thing that we can actually listen to. So this is your traditional TTS pipeline, especially with like neural text-to-speech. So what we're going to be focusing on today is this first part. So text to phonemes. Now, what this means is basically we want to move from characters to phonemes. And we have an example of a phonetic transcription here. So that's, for example, the sentence is, Dr. Smith has 2 cats. And in red, obviously you can see the English spelling. And in blue, you can see the phonetic transcription there. So Dr. Smith has 2 cats. Now the question that we want to answer today is, how do we move from the spelling to the phonemes? So that's how machines process text. And basically, we call this thing text processing. And it goes like this. We start with the raw text. In our case, it's Dr. Smith has 2 cats. Then we do a normalization onto that text so that we get the normalized text. And as you can see, this is an extended normalized version of the initial sentence. In this case, the DR has been expanded into doctor, and the number 2 has been translated into the word 2. So now we have Dr. Smith has 2 cats in normalized form. Now, the next step is to pass that normalized form into a G2P algorithm or model, and that's Grapheme-to-Phoneme. So what's a grapheme? Well, a grapheme is basically a written character. It's a symbol. So we want to pass from the characters all the way to the sounds or the phonemes. And once we go through the G2P process, we get back the phoneme. So Dr. Smith has 2 cats. In this case, like implemented using IPA or the International Phonetic Alphabet. Okay, so that's text processing. And once we're done with the phonemes, next, what we do is we pass those phonemes into the remaining part of the TTS pipeline, as we've seen earlier. So for text processing, really, we have 2 steps. We have normalization first, and then we have Grapheme-to-Phonemes, so G2P. In the rest of this video, we're going to look into some detail into both normalization and, of course, G2P. But why do we have 2 steps, really? Well, normalization handles symbols, dates, numbers, formatting, so that we can get to a normalized version of the text. And then we have G2P. And G2P handles pronunciation. So we basically tend to separate these 2. This is not always true. There are certain normalization processes that are also done by G2P algorithms, and sometimes like the 2 can be conflated. So it's not really a perfect division, but from a conceptual point of view, it makes sense to separate these 2 levels. Okay, so what's the problem with normalization? Well, is that there can be ambiguity. For example, if I have dr, like in our initial sentence, Dr. Smith has 2 cats, dr could be doctor, it could be drive, as in a street, right? Okay, we have 1, 2, 3, and 1, 2, 3 could be 123 or just 1, 2, 3. We also have currency, and that could be normalized as $5.99 or $5.99, for example. Same thing with dates and formatting. If we interpret this date in US daytime, so basically this would be December 5th, but if we use the UK interpretation, this would be the 12th of May. Okay, so here you see like normalization and how it acts. So let's take a look at some of the inputs and normalized outputs. So we already saw Dr. Smith has 2 cats and how it's been normalized. Then we also can see in the second one that we have currency. So it costs and $5.99, and that is like with the currency symbols, and we have to translate that into a normalized output, an expanded output. Same thing with meet at 3:30, and yeah, you can normalize it as meet at 3:30 p.m. or I leave at 123 Main Street. And as you see, the ST dot gets expanded into street, and we also expand the numbers that we interpret in this case as 123. Could also have been 123 Main Street or 123 Main Street. Right, but as you can see, the main problem we have with normalization is that it's context dependent. Like for example, the case of the dr dot, right? It could be doctor, it could be drive, but it really depends on what's around that. So this makes normalization a somewhat quite challenging process. Here are some normalization tools that I use in my day-to-day when I'm working with text-to-speech, or I'm building speech synthesis or voice cloning models. So the one that it's a go-to for me these days is the Nemo text processing. It's a library developed by NVIDIA. It's production-grade normalization. So if there's like one library that you want to use for normalization, just use this. And I'm going to show you. Yeah, so here's like the GitHub repo, and you can use it. Like it's very easy to use, and it works quite well. Cool. You can also take a look at num2words. This is a library, Python library, that does conversion of numbers onto words. So let me show you here. There's the PyPy version of this, or PyPy package. And then I also use Unidecode. Basically what this does, it handles all those like strange symbols and accents. Basically what it does, it's very robust Unicode to ASCII conversion. But most of the time what ends up happening is that you're going to basically use a mix of some of these tools or other tools, normalization tools, and regex as well. Because you may have like some custom rules that you want to use. So in production, at least in my experience, usually what ends up happening is that you use some of these tools and plus like some custom regex on top, because none of these tools actually do like what you actually want to do, like to like a great granularity. This video is offered by myself. If you're building an AI music, voice, or audio products and are facing high-stake technical challenges, I can help. I've been building AI audio companies and products for 15 years. I now offer consulting on architecture, R&D, product strategy, and hiring, so you can avoid costly mistakes and months of wasted time. Visit valeriavelardeadvisor.com to book a strategy call. Link in the description. Now back to the video. Text processing for machines has two phases. There's the normalization part, and we've seen like what that is, and then there's also the Grapheme-to-Phoneme part, and that's probably the most complex part. And now we're going to be focusing onto G2P. So why do we do Grapheme-to-Phoneme? Can't we just use the characters spelled as they are? Well, the problem is that spelling is different from pronunciation in a lot of situations. And indeed, English, regarding like this particular aspect, is quite chaotic. Let me give you a few examples. Let's take a look at these cluster of characters, O-U-G-H, right? So we have that cluster in tough, right? And the pronunciation for O-U-G-H in tough is f, right? Then we have the same spelling in through. And that cluster is now pronounced as U. We also have though. Again, we have the same cluster, but now it's that diphthong O. Or cough. Same characters, but now pronounced in a completely different manner, right? So spelling is different from pronunciation. If you're not convinced, let me give you another example. Read, okay? So in the present tense, I would read it as read, and that's the spelling. But if I'm in the past tense, I still write R-E-A-D, but I pronounce it read. I read a book last week, for example. And then we have B-O-W, right? And so in a couple of examples, we have a bow tie, but we bow down. And as you can see, once again, spelling is different from pronunciation. And that's a problem. Now, I have to say that English is particularly nasty for the difference between spelling and pronunciation. That's one of the reasons why it's so difficult for newcomers who are learning English, especially as a second language, I would say. Other languages are a little bit more forgiving, like for example, Romance languages, like Spanish or Italian, where the spell part, you read it as you spell it most of the time, not always, but most of the time. But it's not really a rule, even like for Romance languages, because like French is quite messy in that respect as well. It's way more similar to English than it is to Spanish, for example. Okay, so, but why G2P then? Okay, so can't we just pass text into this text-to-speech model? Well, in principle we can, as we'll see towards like the end of this video, but traditionally machines have had a hard time reading text because of all of this ambiguity, and it's way better to move from the characters that are like very ambiguous, the spelling that's very ambiguous, to an unambiguous mapping that's also like in sound space, that is like phonemes. With phonemes, we have a one-to-one mapping between a certain sound and a certain symbol, a phoneme. And that's like very, very useful for a machine, because like they prefer like straight lines, things like that are rigid and very mathematical, to things that are more like nuanced and I would say curvy, if you get the analogy there, right? So that's why we go through G2P, and we traditionally don't just stay with characters. So now you may be wondering, but how do we do Grapheme-to-Phoneme? Well, there are a couple of approaches, main approaches, and of course within those approaches you have a gazillion implementation. But on a very high level, you have a rule-based approach where you use like some rules, and you have a learning-based approach where you learn and extract information from data, as in machine learning, of course. Let's jump into rule-based first. So for rule-based G2P, what happens is that you handcraft pronunciation rules that move you from the character grapheme space to the phoneme space. So you have these rules, and you also do dictionary lookups. What is this? This is like a quite interesting one, and I'm going to show you super quick this CMUDict. That's the Carnegie Mellon University dictionary. It has more than 120,000 words. And what it does is that it has a lot of words, and then you can look up these words, and you'll also get the relative phonemes associated like with those words. And you read here alphabet. The phoneme transcription is not done in IPA, International Phonetic Alphabet. That's like the one that we've used so far, but rather in alphabet that uses ASCII symbols. It's another representation of these phonemes, but it's basically like the same thing. It's just like uses like another like alphabet like, to express these phonemes, another like visual transcription. Okay, let's jump into this because this one is really interesting. So here you can look up a word, like for example, hello. We look it up. Here we go. And so here you have the spelling. And down here you have the phoneme representation of that, hello, right? And as I said, this is not IPA, this is alphabet. So these are all the different symbols or the different phonemes we have that represent hello. Good, let's go back. So with rule-based, you usually tend to do a dictionary lookup. If that doesn't work, you fall back to rules for unknown words. Let me give you a visual representation of this. So let's say we do with a rule-based G2P, we want to like find the phonemes for hello. What we do is we input hello. Then the thing like that happens first is a dictionary lookup, for example, using CMUDict as a backend. If hello, if the word is found, then you just get the phoneme. Fantastic, like that's perfect transcription, right? But if it's not found, well, you apply handcrafted phonetic rules. Like for example, O-U-G-H gets transformed into that phoneme, and you get the transcription. But there's a problem, obviously, and I'm sure like you can get that already. But let me give you the pros first. Let's be positive about rule-based G2P. Well, the good things about rule-based Grapheme-to-Phoneme is that like it's super fast, it's interpretable because well, you have the dictionary on the one hand, and on the other hand you have handcrafted rules, so you know why you got the result that you got, and it tends to work well for basically all common words, just because like they are there in the dictionary. So it's just a simple lookup operation, and that's also why it's super fast. But there are cons. So the whole system is quite brittle. It's fragile. It also needs a lot of massive inception, manual effort in order to craft that dictionary, even though of course now we have a lot of these dictionaries already, but in principle like it's a lot of work like to do that, like transferring like from grapheme to phoneme first manually. And the main problem that we have here is that it has like poor generalization. So if a word is not in the dictionary, then it's going to apply handcrafted rules. But as we've seen, those rules are not perfect. It's the O-U-G-H example, right? So where you have like tough and you have cough. So or you have though, right? So the same rule doesn't always apply. So and that's a problem, because like there's like very poor generalization. But then if we can't really encode all the G2P rules manually, what we can do, given we are in an age of deep learning and artificial intelligence, is we can actually learn those rules from some data. And that's what Learn G2P is, right? So we have like some neural models that can learn the transformation from graphemes, from characters to phonemes. So we can treat this GTP problem as a translation problem. So we move from graphemes to phonemes, translating like from one, let's say, language to the other as we would from, say, Italian to French or English to Spanish. And what are the usual architectures that we use when we do this, like machine translation, where these are sequence-to-sequence models? So in the input, you have a sentence, say, in Italian, and you have as output, as target, the same sentence, but now in French. So we can use this sequence-to-sequence architecture, and we can train on words, phonemes pairs, characters and phoneme pairs, as we would in the case of translation, where we would have a pair in the original language, say Italian, and then the translation of that sentence in French, for example. So let's take a look at the workflow that we can apply for these models, these learned G2P models. So the input is always the same. So it could be like a single word or a sentence, right? And then what we do is we pass that through an encoder. The encoder could be a transformer or LSTM encoder, and what it does, it just like it squeezes down all the information in the sentence into an embedding that has like some context about like the word and the sentence, and then we can pass that embedding into a decoder. Once again, it's the decoder part of a transformer or an LSTM. These days it's usually a transformer. And at the output, we would actually get hello, like written like in phoneme format, in this case alphabet. Okay, so that's basically the idea. And the architecture, if you look at it, it's basically an encoder-decoder model. Most of the time, today, we would use a transformer model. And this is the vanilla transformer. So here on the left-hand side, you have the encoder part. On the right-hand side, you have the decoder part. And that's like from the original paper, attention is all you need. And I won't describe the details of the transformer model because it goes beyond the scope of this course. But if you're not familiar with this, I encourage you to watch a couple of videos that I made about transformer. It goes into the nitty-gritty details of the math and the intuition and everything. So you'll find the first one up here, and you can then watch like the second one in another series there. Okay, so now what are the pros? What are the strengths of G2P models that use neural networks? Well, among the pros, you have that they are able to learn complex patterns, and they're able to generalize to unseen words, which is a really, really good thing. And that's what rule-based G2P algorithms struggled with. But of course, there are some limitations and some cons as well. These models, as usually in deep learning, requires a lot of data and paired data. You need the phonemes and, well, the graphemes and the relative phonemes. It's slower, it takes more time, obviously, than a simple lookup. And it can be difficult to interpret. And the reason is because, of course, it just like learns the rules internally. So these rules are not explicit in a sense. And for certain applications, this could actually be a limitation. Okay, now let's go back to the ambiguity problem. And let's take a look at this sentence in particular. I read books every day. The spelling is read, as we have like the word there in bold. The pronunciation is read. And in the second sentence, I read a book yesterday, and you see the phonetic transcription there. Yes, there's ambiguity there, and we already saw this one, right? So you have the same spelling, but then the pronunciation is different, well, in this case, not only the pronunciation is different, but also the meaning. The one is present tense. In the second sentence, you have the past tense. So, well, that's basically the problem that we outlined earlier. Same spelling, different sounds. If we want to give it a proper academic name to it, these are homographs, and these are words that have the same spelling, the same characters on paper, but they sound differently when we pronounce them. So how can we solve ambiguity? Well, in rule-based, there's an approach that you would use if you were like a very knowledgeable about language in general and you knew like all the grammar behind. What you could do is you could basically analyze all the words one by one and get an idea of the type of the part of speech that each word belongs to. Like, for example, I is a pronoun. Read is a verb in the past tense, and you can move on and on, but I'm gonna just like stop here. So we do a grammatical part of speech analysis of the sentence, and so once we get the part of speech there, we could have a rule that says, hey, if read is in its past tense, then the actual pronunciation for it, the phonetic transcription is read, it's not read, okay? So basically what we do here is we would use a part of speech tagging, but that comes with a cost, and the cost is that it requires a separate POS, part of speech tagger. The accuracy for homographs for part of speech isn't necessarily like all that great. You could also use an easier rule that just says, hey, just like pick the most common pronunciation for that particular word, that, well, not word, but that particular grapheme that you have there, right? Of course, it's going to fail, but also like the part of speech tagger is going to fail because accuracy for homographs isn't really that great. So yeah, this is potentially a solution, well, or at least like an initial heuristic that you could use to solve ambiguity with a rule-based GTP. But there may be a better way of doing this. So can you think? So how would you, and how do you personally differentiate between two sentences, like I read today or I read a book yesterday? So how do you understand the different pronunciation? How do you understand the fact like that those two R-E-A-D have different pronunciations and are actually present tense and past tense? Any ideas? Well, it's context. It's from context. So we learn to differentiate by looking at the sentence and the word in the context of all the other words before and after that word. And that's what we can do in learned GTP models. So we could use context-aware neural models. So what does that mean? Well, we could use like what we call bidirectional architecture, bidirectional context. So take a look like at this sentence, like that we've seen already. So I read a book yesterday. We pass it through a bidirectional encoder. So what the encoder does, because it has a bidirectional architecture, it looks left and right of the current word analyzed for context. And so it comes up with an embedding for each word that has contextual information. It knows what happened before, it knows what happens next, and the relationship among all of those words. And then basically once we have like that context embedding, what the model can notice, can learn to notice, is that there's yesterday. So if the model is analyzing the word read, in this case read, then it can pick up on a certain signal, that is the adverb yesterday, and yesterday signals that the act of reading happened in the past. Okay, and so because of that information, now we know that the read is not pronounced as read, but it's read because it's a past tense. And indeed, all of that information gets sort of embedded into this contextual embedding extracted from the bidirectional encoder. So now we pass that context embedding into a phoneme decoder, and we get the right correct transcription. That is, I read a book yesterday. So there's a mistake here, right? I read the book. It's not the book, it's a book yesterday. Cool, but I think like you got like this idea of bidirectional context. So how do we solve ambiguity? Well, we can solve it using this bidirectional architecture. And specifically, what I do like in my line of work, like most of the time, is I use a pre-trained language model, like BERT or all BERT variants, like Roberta, for example. So what's BERT? If you haven't read this paper or like learned about this model, I really encourage you to do so, because it's a pillar that came out in 2019. So BERT is a pre-training of deep bidirectional transformers for language understanding. So this is an encoder model. It's a transformer model that only has a bidirectional encoder architecture. You cannot really use it for generation, but it's great for understanding because of the encoding architecture and the bidirectional architecture. What it does, it really understands subtleties in language. It understands context, meaning, and relationships among words. And so this is a great model for use cases like text search or classification, like for example, topic classification, sentiment analysis. Okay, but how do we use it? Well, it's quite simple, right? So we use BERT as the encoder in our workflow, right? So we have the initial sentence, we pass it through BERT or any other pre-trained language model. And then we extract the context embeddings for each word, and then we pass that through the phoneme decoder, and so hopefully we'll get a nice transcription, a correct transcription, phonetic transcription of the original spelled sequence or sentence. Okay, but of course there's always room for improving these GTP models, right? So we could think of like more elaborate models that help us solving the ambiguity problem even more, but we don't always have to. In a sense, throughout this video, I lied to you on purpose, because traditionally we've always used this text processing, the normalization, as well as GTP, Grapheme-to-Phoneme. But in more modern text-to-speech pipelines, sometimes we just don't need GTP at all. And well, how's that possible? Well, because some modern end-to-end text-to-speech models basically go through text, directly the characters, into the end-to-end model, and they spit a sound, or like a waveform, out of it directly. So everything is learned implicitly, directly in the end-to-end model, so that you don't need an explicit GTP model. And that's, for example, the case for tachytron 2, That's another very important text-to-speech model that came out, I believe, in 2018. Yes, 2018. It basically does like a condition, it uses like WebNet and MEL spectrograms for generating speech. But the point is that you just pass text in and you get a waveform output. So that there's no G2P, there's no, because all the Grapheme-to-Phoneme transcriptions are kind of learned internally by targeting. So there are certain end-to-end text-to-speech that do use this approach these days, but still, even like today, there are like other models that just use the more traditional approach where you actually do like the initial text processing. Okay, so let me share some of the G2P tools that I use when I work with voice cloning or text-to-speech. Of course, we have the Carnegie Mellon University Dictionary with a lot of phonetic transcriptions for more than 100,000 words. We already saw that. There's also this really cool Python library. It's called Phonemizer that has multiple G2P backends. So you can see it here. It has all of these backends that actually, these are the models that do the Grapheme-to-Phoneme transcription for you, and some of these like support up to more than 100 languages. So it's a quite solid library. Then, if you want something like quick and dirty, like for English, I highly suggest you use G2PN. This is a hybrid model. It works really well. Most of the time I just use this. It works fine. Basically it does an initial dictionary lookup, and if that fails, the fallback is not towards like handcrafted rules, but rather to a neural model. And here you have the library on PyPy. You also have Epitran. This is another like quite solid G2P model. You can use it like with more than 60 languages. So yeah, it's quite impressive. So you have like Turkmen, you have Zulu, you have a lot of languages. And finally, there's a DeepPhonemizer. That's a deep learning based G2P model. It actually uses transformers. It's quite flexible, it's quite powerful, and I've used it successfully multiple times. Again, you can find it here. You have like all the resources in the slide presentation. And by the way, you're going to have access to this slide presentation if you go in the description box below and just like look it up like on my GitHub. So you'll have all the information there. My point is, play around with all of these resources. You can really like plug and play with them. They're really easy to use, but I encourage you to play around with them because you're going to get like a better feel for how they work and the difference between spelling, and familiarize also like with phonetic transcriptions, which is fundamental for operating in voice cloning and text-to-speech. Okay, so what have we learned today? A lot of things, but here are the most important ones. So we can think of text processing within text-to-speech as divided into two main parts. One is normalization, where we move from like the symbols and we expand them into full normalized words. Then we have G2P, where we move from words, from characters to phonemes. There are two approaches for G2P, and the first one is rule-based. That's quite fast, but it's a little bit like rigid, and it's mainly a dictionary lookup with some fallback handcrafted rules that don't really like work that great. And then you have another path that is using most of the time deep learning, so you learn from data. This is way more flexible. It is context aware, especially if you use bi-directional architectures for encoders and pre-trained models, language models like BERT, and of course it's data driven. Finally, the most important part is like to have a really solid production level text processing framework is to resolve ambiguity. So you have to resolve all of those like homographs. And how do you do that? Well, in rule-based, you can use part of speech tagging or simple heuristics. Like for example, yeah, I'm gonna just select the phonetic transcription that's the most common. It's not gonna work, obviously, but it can work sometimes, right? And for ambiguity resolution in learning models, you can use bidirectional context and pre-trained language models like BERT, as I said. Hope you had a lot of fun learning about how machines process text. If you found value in this video, please do give a thumb up to the video so you'll help me with the algorithm. That's all for today. I'll see you next time. Take care for now.